Hello, everyone. Welcome back to the AAS YouTube channel. And this one is going down the ebook series. And I'm very happy to have ebook author Nikku Madhusudhan with us today. Hey, Madhu.
Hi, Frank. How are you? Good to see you.
I'm doing well on this December 20th of 2021. So we're coming up on the winter solstice and New Year celebrations. And so I wish you the best. I hope you have a great winter solstice and New Year celebration.
Thank you. Same to you.
And where are you located at, Madhu?
So I'm at Cambridge, UK right now.
Okay, very good. Is there snow on the ground yet?
Not yet, no.
Does it snow there?
Hoping, yeah, it does. I mean, in the winter.
Okay.
We might have to wait another few weeks, or I mean, it does snow.
No, January, a little post New Year's 2022. So very cool. So it is still, well, it gets relatively cool here in the morning. I'm in Phoenix, Arizona, and so we'll get down to, a few degrees above freezing in the morning, and then it'll warm up to about 70 or something like that in the day. So it's quite pleasant overall. Got to wear a jacket though in the morning. So I imagine it's jacket weather there in the UK.
Oh yeah, sorry, not quite. Not quite, maybe. Yeah, so it does get to we're still on a few degrees Celsius sort of temperatures throughout the day here.
It's amazing how we bounce between Kelvin, Celsius, and some of us in Fahrenheit. It's all great. Madhu, what do you like to do for research?
Yeah, so I work in the general area of exoplanets, but my specialization is exoplanet atmospheres. That's my main area of research, but I also work in interiors and a little bit of connections between atmospheric compositions and planet formation. And most of the time we do theory. So I lead a group here on the topic. We do theory, but we also do observations in specific areas.
Very cool. That's a hot topic these days, of course, is exoplanet atmosphere characterizations. Very cool. And that is going to bring us to this very lovely ebook. So I'm going to do a screen share at this point. This is a brand new one. I think this one just came out, yeah?
Yeah, just 2 months ago.
Yeah, 2 months. So this is a hot off the press, folks.
Absolutely.
Yeah. So Exofrontiers. Big questions in exoplanetary science, and Madhu, take us away.
Yeah, so this book is an effort to bring together some of the big questions in the field of exoplanet science, and the motivation is that oftentimes one hears about how how exoplanet science is a forefront area of research. We all hear this, that there are big advances being made and all that. But for most people, what is not clear in my experience is that what specifically are the questions we are trying to tackle. Beyond the obvious is that life elsewhere. But that's not all that we are about. It's not just about finding life at the end of the day. Yes. So the motivation really is from that sort of a sentiment is, can we come together as a field and identify what are all the areas in the field and what are the big questions in each of those areas. Now, the motivation was also for this particular book is based on a series of meetings I chaired between 2016 and 2019. Called the Exofrontiers Symposia, supported by the Kavli Foundation here at Cambridge.
Nice.
So each of those meetings had focused on a different topic, but the general theme of these meetings were also the same.
Okay, so I have a question then. So just on the pragmatic. So when did the idea, or when were you approached about doing this ebook, and how long did it take to finally come out in this form? Was this a 2-week process? Was it
No, not quite.
Not quite? Okay.
So around 2017, 2017 is when we went through the signing of the process, of the contract for the book. I was approached by IOP, for a book on exoplanets, and I think the idea was a specific book on exoplanet atmospheres, or some specific area. And this wasn't the original motivation, but then I happened to be running this series of meetings at the time, so I thought maybe it might be better if we focused on this pan field sort of effort to bring together various areas and identify these questions, which was also the focus of the meeting. So that's how they sort of originated. Cool. And then the book actually started, it wasn't clear because it's got such like an open-ended feel to it. Mm-hmm. It took me another year just to sort of think of the strategy, if you will, to put together these various areas. So it was not trivial. So we didn't actually start working on the book until like maybe 2018-ish.
Okay.
It took another year, and by that point, like a couple of meetings had happened, and I had a better idea of a sense of direction. So 2018-ish is when we started. Invitations went out to various colleagues in the field. The one thing very special about this book is that each chapter, these are not review papers. So there are 24 chapters in this book, covering most areas within exoplanet science. I would say almost all areas. There would be a couple of areas which may not be well represented, some more than others, but most areas are covered. But any of these chapters, you can be confident, is not like a normal review paper, an extensive review paper. Instead, the remit was very clear, and it was made clear to the authors, is that you only focus very briefly on the introduction and state of the art, very briefly, a page or two, but then focus mostly on what are the questions, big questions in that area, and what are the challenges and opportunities. Okay. So the remit is very specific, and the authors have all done a wonderful job. So we invited a few top experts from each area. And sometimes the chapters are single author chapters, and sometimes there are a couple of authors coming together, and these are all top experts in their own areas. And then it's supposed to portray their vision of the future landscape of the field, basically. So it's very organic in that sense. So that's what we did, and it was quite a successful activity, I would say.
Yeah, so about 4 years from
yeah, I mean, from the time people actually started, and different invitations went out on different time scales, but overall it was about 3 years, I would say, from start to finish, between the various chapters.
Very cool. Did you get any slowdown from the pandemic?
Yeah, towards the end, there was that issue. The pandemic did spring a surprise on all of us. So there was some slowdown towards the end, but the activity was already in pretty decent shape by that time. So we did what we could.
Cool. So let's go ahead and take a look at some of these 24 brief chapters. Exofrontiers, big questions. Editor-in-chief of the journals, Ethan Vishniak. There's our 7 corridors, SS. There's the advisory board. Steve Kowaler heads that up on the advisory board. Exofrontiers, IOP Publishing. To the Human Quest for Worlds Beyond. And contents, here we go.
Yeah, so so these, we divided this whole book into a few broad areas. So I start with, a broad brush of the whole field, just to lay out the landscape and identify the few very top level questions, generally speaking. And then that sort of, gives the direction for what's coming in the remaining chapters. So there is the introduction, and then there are observational. There is one part that is all observational, demographics, detection, spectroscopic observations, and so on. So part 2 is all observations, various topics within that. And then there is a theory and characterization, be it dynamics or the circumstellar environment, planet formation, we'll go through these in a little bit more detail in a second. And then atmospheres, interiors, all sorts of things that are theory related. And then we have a part, the part 4 is on habitability and biosignatures. One chapter on each. And then we end with this future-looking chapter on the holy grail, so to speak, of the field of the search for spectroscopic science of life by Sarah Stiger.
Right.
So that's the layout of the field of the book, and we can go through very briefly through each of those chapters. In the landscape chapter at the very beginning, what I've identified here, and this is commonly agreed upon, is that we are in the field of exoplanet science, where we have 3 broad questions that we are trying to answer across the board, starting with planetary diversity. When we are discovering these numerous planets, thousands of planets, the very obvious thing that, sort of the first sight we get is one of diversity.
Right. It doesn't look like ours.
Exactly. So the very first impression we get in exoplanet science is that, where are we in this picture? We don't appear anywhere like the solar system.
Out here.
You would think for millennia, there is a philosophical, it's a deeply philosophical realization as well, is that we as a species for thousands of years have been, thinking about worlds beyond, and more recently looking for worlds beyond. And the first planets that we found nearly 25-30 years ago are nothing like what we see in the solar system, right? So that right there, we started off with those extreme sort of oddballs that there was no concept of from our solar system experience. Be it planets around pulsars, or the hot Jupiters around sun-like stars. These have we're so contrary to our view of planets and planetary systems. And from there on, what we have seen in the last 2 decades is even more extreme diversity, right, on all scales. So today we know of planets all the way from Earth size and even slightly smaller planets and to super Jupiters. There is no, in the solar system, if you look, there is a quantization. There are the terrestrial planets, there are the ice giants, and then there are the gas giants. But in exoplanet systems, there is no quantization. It's almost a continuum in all properties you can think of. Right. So in that subsection there, I talk about that and what are the, what are we after in the search for diversity. And then another big area that almost predates exoplanets is planet formation. Yep. How do planets come about? And that has motivations from solar system science itself, right? So how did the solar system originate, and how did the different types of planets form, migrate, their evolutionary histories and so on, have been open questions since before exoplanet science. And exoplanets have only intensified that, that area, because we are finding even more extreme examples of where planets can form. So that is another big area in the exoplanet landscape. And then the third big area is the obvious one, which is the holy grail, so to speak, of the field, which is the search for life elsewhere. Yep. So I touch upon some key developments in recent years in all these areas, and that's more a way of introducing the various chapters that are coming next, just to lay it out for the reader. And then we enter into the actual topics written by various colleagues. So at the outset, I must say this is a huge, collective effort by all the authors. So I wrote the introductory chapter, and I was a co-author on only one of the chapters, the atmospheric modeling chapter. But most of the contributions came from our colleagues, very esteemed colleagues from various areas of the field, who gave their generous time and effort to make this happen. There are over 40 authors here, so which is very which is important to note, their contributions to this effort.
Absolutely.
So in transit service, we start with the demographics of exoplanets led by Scott, and Michael and Jesse. This chapter talks about what are the big questions in our understanding of exoplanet demographics. The format of all the chapters is pretty similar to most extent. We have given, the authors obviously have all the freedom to, shape their chapters however they want. But what was requested of them is that we spend very briefly on the introduction, not too much on the introduction, just very brief, and then you can point to review papers and so on. There are other venues for that, but then go straight into what is the state of the art, what are the important questions and goals we are trying to seek in that area, and then what are the challenges and opportunities. So you'll see that sort of pattern repeat through all the chapters. And in demographics, that is what has been done, is that what do we know about the current demographics of exoplanet systems, and what are still some of the open questions in this area, and what are we seeking. And now demographics is interesting because exoplanet demographics doesn't come from one method, right? So it comes from all sort of discovery tools that you have at your disposal in the field. And that includes transit surveys, radial velocities, direct imaging, microlensing surveys, all kinds of techniques. So they did a great job at identifying what are the big questions that are still remaining, and what are some of the challenges in pursuing those questions. For example, if you are seeing a certain mass function or certain distribution, so how does that depend on various other factors that might influence it, be it selection biases or observing techniques or whatnot, and what parts of that parameter space of the demographics are still incomplete, so to speak. So there are observational and intrinsic observational challenges, intrinsic biases, all kinds of things that affect planetary demographics, and our authors here have done a great job in laying it out for the reader. And then we come to transit surveys, and as you know, the transit technique has been the most successful technique in discovering planets to date, in just sort of the sheer numbers, thanks to major surveys, space-based surveys like Kepler and now TESS and CRO and so on.
Pluto soon.
Yeah. And then Plato will be towards the end of towards the end of this decade, well, like mid-ish decade. So there's a lot happening in transit surveys. This chapter, led by Don, and with major contributions from Natalie, Magali, and George, gives that sort of view, bringing results from different sort of surveys together, and summarizing what have we learned from our transit surveys, and what are we still expecting to learn, what sort of planetary statistics that we get, demographics that we get from these specific surveys, and what are the challenges for completeness of these of those kinds of planets that are detectable via transit. I mean, it is understandable that the parameter space, the planetary parameter space, is such that some techniques are very good at finding planets in some regions of the parameter space. Right. So what is accessible to transits is not necessarily accessible to direct imaging, for example. Right. So that is the motivation for having individual chapters for each of these different areas. And within these, there are, as I already said previously, there are technical challenges in each of these surveys. For example, if you want to find transits of Earth-like planets around Sun-like stars, that's very hard. Even though we have found thousands of planets, but getting literal solar system analogs is still a challenge with transit surveys. So the Plato mission has that as one of the main goals of the mission, is specifically to look for Earth-like planets around Sun-like stars. Right? But that that demographic is not complete yet. We don't have an exact solar system analog with multiple planets at similar, separations and so on.
Regular separations.
Right? Yeah. So the transit, so the farther you go in orbital separation, the harder it becomes for transits and so on. So that chapter does a great job in talking about these various aspects, multi-planet systems and so on transit surveys. And then we come to radial velocity surveys. That's a chapter led by Deborah Fisher. And this is talking about, so the radial velocity technique was the first technique used to detect a planet around a sun-like star, going back to the famous 51 Peg discovery in 1995. So previously, until about mid 2000s, radial velocity surveys were still the dominant mode of planet detection. So most planets we knew at that time, until that time, were discovered by radial velocities.
Yep.
You had a question?
No. Yep. I'm agreeing with you.
Yeah. So until then, like RVs were the dominant method, but then transits came along and took over very quickly with all these space-based surveys, mostly by space-based surveys. But then the radial velocity technique still plays an essential and very central role in exoplanet characterization, exoplanet detection and characterization, in the sense that you still need the RV for mass measurements, for accurate mass measurements of these planets. So RV has been playing a huge supporting role to the planets detected by the transits, because the transit method only gives you the radius, not the mass. I mean, there is an indirect way with transit timing variations and so on to get mass constraints in multi-planet systems, but RV is still the mainstay, the main method for mass measurements currently. So that's all discussed in the chapter, and what are the big challenges we have, especially with regards to the extreme precision radial velocity efforts that are happening in the field right now. The reason for that is that if you want to detect an Earth-like planet around a sun-like star, the RV signal is tiny, right? It's of the order 10 centimeters per second. And that is a challenge, not least because the stellar effects themselves are at that level, roughly. So there are various challenges and efforts going on in the field, and that chapter addresses these sorts of challenges and what the opportunities are on the path forward.
Cool.
So that's that. And then we get to direct imaging and spectroscopy. Now, the thing with direct imaging is that you get both the planet detection and the atmospheric measurement in one go, almost. You get the spectroscopy. If it's a spectroscopic instrument, you get it for free.
Right.
Because what you're detecting is light emitted by the planet itself. If you're looking in the infrared, you get thermal emission. If you look in the optical, you get reflection. But you're getting the atmospheric signature and the planet almost in one go.
Right.
So that those two are combined here. You'll see that for transits, there is a separate topic on detection, and then there is another topic on transit spectroscopy coming after.
Yep.
But for direct imaging, we combined those two chapters into one, led by this excellent team of authors here, starting with Sasha Hinckley and various other colleagues from within the field. And this chapter covers the state-of-the-art observations happening in direct imaging. Of all these observing techniques, direct imaging is the youngest.
Yes.
The first detections were made around 2008. So about 13 years ago, but the quality of the observations you get are spectacular, I must say. Some of the spectroscopic data that you get, there are few planets, order 10-ish planets detected by direct imaging, but the spectra you get from those tend to be very good, at least for a subset of those, and direct thermal emission spectra, which are great to quantify their atmospheric compositions as well.
Cool.
So that chapter goes into all the things that are happening at the frontier and what are the big questions in that area. Because as I said with the transit technique, the direct imaging technique also probes a specific region of the parameter space, you see, mostly like distant orbits, planets on large orbital separations. So many of the questions for that particular area are concerned with, how do you ensure completeness? How can you get closer and closer to smaller and smaller planets and so on? So many of the big questions are surrounding those inherent limitations of the method, and also technological challenges, because this is technically very challenging observations. The planets are contrasts you expect are very small.
Right.
Okay, so then we have a short chapter on small star opportunities led by Omri Triod. This is going into the opportunities provided by M dwarfs for detecting small planets.
Yeah.
When the star is smaller, it makes it favorable for detecting small planets, both by the transit technique and also by the RV radial velocity methods, and also for atmospheric characterization. So there are various positives there. So that chapter goes into all those aspects. We are talking about, for example, TRAPPIST-1 system that you may have heard of is a poster child of that sort of those sorts of opportunities. So we have one chapter on that. And then we go into transit spectroscopy. This is atmospheric observations, spectroscopic observations of transiting planets. There has been huge amount of progress on this topic, over the last decade. Most of the atmospheric observations we have today come from transit spectroscopy, and we have learned a great deal, both through space-based and ground-based observations of transit spectra, both in the optical and infrared, and UV as well. So that chapter goes into detail on that topic and talks about what are the big questions that we are seeking to answer, especially with the James Webb Space Telescope right around the corner.
Yeah.
So this is a very good time to be having this discussion we are having here with JWST close to launch in 5 days, 4 or 5 days.
5 days, crossing.
Fingers crossed. So that way I feel very lucky to be sitting here talking about the developments in exoplanet science with JWST about to launch.
Finally.
Super.
Very cool.
Okay. So then we go into high resolution spectroscopy. So this is this is a technique that allows us to characterize atmospheres of planets, both transiting and non-transiting, and even directly imaged planets to some extent. Okay. Mostly by looking at the Doppler shifts of the planetary spectra as they move in their orbit. And this is a very promising technique that has taken off just in the last decade, actually. There are a small number of planets, less than about 10 planets, but then the kind of detections you get, chemical detections you get, can be pretty robust this way. And these sorts of observations also get over some of the limitations inherent to the other techniques. Let's say the transit technique, for example.
Nice.
So Matteo Broghi and Jane Berkby, top experts in that area, did a great job again in going into the details of what's the promise of this technique and what are the big questions. And then we move on to 2 chapters just outlining mission level opportunities that are on the horizon. One of them, the space missions for exoplanet science, is a big chapter, but the authors did a wonderful job, I must say. Carl, Heike, Aki, and Ave did a wonderful job of summarizing all the missions, past, present, and future missions that have anything to do with exoplanet science, space missions. I think it's a wonderful chapter putting everything in context, and future mission concepts like the LUVOIR and HABEX and Origins and so on. So they did a great job in putting things in perspective on what did we get in terms of like fundamental knowledge from the previous missions and what is on the horizon, including JWST, and what is coming. So I think that, that's a great chapter. They had a lot of work on their hands in summarizing that, because we know how many missions are coming.
Yeah.
In this decade, everyone in exoplanet science would know that this decade is going to be that sort of a golden era of exoplanet science in terms of just the amount of data we're expecting.
Yeah.
Right. I mean, with JWST right around the corner, there will be within this decade 3 space missions for just atmospheric characterization. HST is there, is operating. Obviously, that's our main workhorse right now. But then there will be JWST, and towards the end of the decade, there will be aerial, all for atmospheric characterization.
Right.
And same for detection, right? There, K2 and TESS have been operating very well, and KOPS has just been starting getting good data, and then there will be Plato very soon.
Yep.
Right. So both on the detection front and from space and atmospheric characterization front, there is a lot going on. So that's a chapter that summarizes all of that. And then small satellites. This is a niche area which has been taking off just in the last few years on how CubeSats can contribute to exoplanet science, for various reasons, not least of which is the fact that they're cheap by definition. So this chapter, led by Luca, Peter, and Ian, go into some of those questions on how can we leverage small satellites to contribute to exoplanet science. Right. So can they be complementary to the larger missions, both in the exoplanet detection aspects as well as in the characterization aspects? Okay. So that's a very interesting topic, and they have some interesting new ideas as well, and how we can leverage them best.
Some frontier stuff there.
Yeah. So all of this is absolute frontier stuff, and so we have only covered, in all this time, we have only covered half the book, all about observations, you see. And then we go into exoplanet theory and characterization. And you can imagine the theory landscape to be just as diverse as the observations.
Indeed.
And I can break this down into a few broad topics, in terms of theory. One obvious, just from the planet detection, one obvious aspect one can characterize is the orbital architectures of the system themselves. Yep. And what are the orbital dynamical processes that one can constrain from these sorts of observations, be it the resonances or the obliquities of the systems, or just how the systems are compact in nature, and the multiplicity and so on, the arrangements. So that chapter led by Dan talks about that, as well as putting the solar system's architecture in context. That's a very important aspect of exoplanet orbital architectures, is how unique is the solar system architecture, and we haven't found that many yet that are very similar to the solar system. So that chapter goes into detail on that. So orbital architectures is one thing we can get, and then from the macroscopic properties and bulk properties and various other observations one can make of the planet's disks themselves, of the planet forming disks and debris disks. A big area of theory is just planet formation and evolution, right? So we have a number of chapters focused on that topic, starting with the theory of planet formation, led by Ravit and Alessandro Morbidelli, talking about various planet formation processes, from planetesimal formation to forming the planets themselves, that entire sequence of processes, and what are the big questions at each of those steps along the way. So they do a great job in going through that whole thing and identifying what are our opportunities in constraining those processes. Cool. And then John Papalagio talks about planetary migration, focusing mostly on migration through the disk, in where these planets are forming, and talking about what we know so far, and what is coming. So that area, planetary migration, is one of the oldest areas of theory of exoplanet science, all the way from finding hot Jupiters.
Yeah.
You see, like, if you want to explain hot Jupiters that close to their orbit, some form of migration must have happened, right? Because, like, generally one would think that close to the star, we are talking about 1/10 of the distance to the star than Mercury is to the sun. It's very hard to find the raw material to make a supergiant planet.
Right
there. So the planet must have formed elsewhere and migrated to some extent. So how that happens is the content of that topic, and that's been there for more than 20 years. Like, people have been discussing that for 20 years now. And John's chapter on that puts it all in perspective.
Nice.
And then we get to astrochemistry and planet formation, and this is a very happening topic right now with spectacular observations made by ALMA of planet forming environments, and also tying it to chemistry that we see in planets themselves.
Right.
So this chapter does a great job in talking about a little bit of planet formation and how the chemistry operates within planet formation, and how that may be tied to planets and their compositions. So that whole pathway from the cloud to the planet, from a protoplanetary, protostellar cloud all the way to the planet, is the content of that chapter. And they talk about highlights in our observations of protoplanetary environments as well. And how we are mapping ice lines and so on. So that's a great chapter, I thought, led by Evina and Ted Bergen. And then we also look into debris disks. These are the remnants of planet formation process, if you will. So you have the planet, but also there are various remnants of the planet formation process. So Mark's chapter talks on debris disks, talks about all the various things you can constrain from current observations of debris disks and what you can learn about planet formation that way. Okay. Those are the contents of the chapter are clear there. It talks about constraints on planetary system architecture and evolution from the debris disks, and how planetary bombardment works, and what we have learned in that area, and planetesimal compositions and so on. So when I said, in the theory landscape, we have dynamics, we have planet formation, dynamics and architecture, we have planet formation, and then we have the planets themselves. And these next few chapters are all about that, talking about the planets themselves, their interiors, their atmospheres, and within atmospheres, because atmospheres have grown to be, exoplanet atmosphere, to be such a huge topic now. Right. We had to break it down into a few areas as well. And those are all the areas that you see there. So we start with exoplanet interiors by Nadine, Nettleman, and Diana Valencia, who talks about all the open questions and our understanding of planetary interiors from their bulk parameters largely, and what sort of constraints can we get and what can we learn in the future with upcoming facilities. And then we go into exoplanet atmospheres, and in the first chapter there we lay out the general modeling and retrieval frameworks for atmospheres. And those are two aspects. One is, what are the challenges in forward modeling of these atmospheres and their spectra, and what are the challenges in retrieving the atmospheric properties given spectroscopic observations. So those are the two broad areas that we cover there. So this was led by Jonathan and Joanna. Joe Basto and I contributed to this chapter as well. But those are the kinds of things we talk about in that chapter. And what are the open questions in exoplanetary atmospheres from a theoretical standpoint, be it chemical disequilibrium or chemistry, we talk in the next chapter, but we just lay out the top level questions in that chapter.
Right.
And then we go into a little bit more detail on each of the individual aspects. So atmospheric chemistry, led by Julie Moses, talks in great detail about all aspects of equilibrium and non-equilibrium chemistry across the planetary parameter space, and what are the big questions? Why fundamentally do we want to understand chemistry? Covering two broad aspects. One is chemical processes, atmospheric processes in these atmospheres, but also tying these compositions to planet formation.
Yeah.
Again, so this loops back to the astrochemistry and planet formation chapter. So we build some interconnections like this, and Julie did a great job here again in setting that that scene. Okay, and then we talk about atmospheric dynamics. This is atmospheric circulation, led by Adam Showman. This chapter talks about in great detail all aspects of atmospheric dynamics, all the way from giant planets, for which we have very detailed phase curves, phase result spectroscopy, to small planets for which we don't have data, but what should we expect in the future to learn, as well as brown dwarfs, like non-irradiated planets and so on. So atmospheric circulation, basically. Now, I should mention here, I owe a great deal to Adam Showman, a great colleague and friend. Just after he had submitted, not like while this book was in preparation, last year actually, in early 2020, we learned, sorry about that. Okay. So we learned that Adam passed away in early 2020. So that was very sad. Very sad, but I'm really thankful for everything he gave to the field, and he was a major figure in atmospheric dynamics, one of the pioneers of the field.
Thank you, Adam.
Yeah, and then we come to clouds. As we all know, in exoplanetary atmospheres, clouds is a very important topic for atmospheric observations or atmospheric characterization of exoplanets. Christian, who's a top expert on cloud microphysics, led this chapter. And this chapter focuses mostly on microphysical processes and how we need a holistic understanding, holistic approach to understand clouds in exoplanetary atmospheres from a microphysical point of view. Microphysical cloud modeling point of view. So that's what that chapter is about. And then I wanted to bring the attention in atmospheric characterization to the importance of molecular and atomic line data, because which feeds into the spectra that we model. So Sergey and Jonathan did that. So they lay out the state of the art for what sort of line data is currently available, what are the important questions that we are seeking to answer in that particular area, and what are the molecules, the species for which we need more data and more efforts are needed. For example, line broadening parameters are required and so on. So there are various technical challenges in this area, and they do a great job in laying it out as well.
Yeah, and this touches the topic of laboratory astrophysics, things we can do on Earth to.
Absolutely, and which is very important for interpretation of the observations.
Absolutely.
So that's the theory landscape, and then we enter into our last stretch of the book, which is the habitability, talking about the ultimate question of the habitability and search for life elsewhere on exoplanets. And so there are two chapters here, one on habitability, one on astrobiology. The habitability chapter, led by Jim Casting, talks about what we know, what we think we know in terms of planetary habitability, because we have exactly one data point in the universe, that is our own Earth. And Jim is a pioneer in studying of exoplanet habitability. He was one of the early proposers of the habitable zone, the terrestrial habitable zone. So he goes into great length on what makes planets habitable and what are the challenges to habitability and our understanding of habitability in exoplanetary systems across the wide range of planets that we see out there, and that we expect to see around a wide range of stellar types, from sunlight to M dwarfs. right? So he talks about some of those very difficult questions on, the fundamentals of what makes a planet habitable.
Cool.
So that's a cool chapter. And then we go into astrobiology, led by Vicky Meadows. There is a little bit of overlap between those two chapters, as inevitably you would expect there to be. So she also touches upon habitability, but from an astrobiology point of view, in terms of how do you, so your planet can be habitable, and then is it inhabited, and what sort of processes and environmental conditions affect life on planets, and what sort of biosignatures may we be looking for, and what sort of false positives might there be in detecting life elsewhere. So again, Vicky has done great work in this area, another pioneers in astrobiology, and she again does a wonderful job in writing, in laying out what the big questions and opportunities are there in that topic. And then we get to the grand finale of the book by talking about what the prospects are for our searches for spectroscopic signs of life. So the goal is very specific, right? We want to detect a biosignature in the atmosphere of an exoplanet, right? So this chapter highlights all the opportunities that are on the path to attaining that goal. Cool. And then what are the challenges in getting there? So that sort of gets us to the answering the holy grail of the field, which is ultimately we want to detect life elsewhere. But from start to finish, the book does everything else in between.
It's a process.
Exactly. So that's it. So that's the full extent of the book. And I couldn't thank enough all my authors on this book, who have done a wonderful job, who are all stalwarts in their own areas, but who have kindly agreed to give their time and effort to really bringing out the best the field has to offer in all these areas.
Very nice, very nice. Madhu, thank you so much for walking us through your new ebook, Exofrontiers, Big Questions in Exoplanetary Science.
Thanks, Frank, for having me here, and it was a pleasure talking about this book. I hope the readers enjoy it, and it should be accessible to graduate students and even to senior undergrads. So anyone who is looking to start research, be it like senior undergrads to graduate students, or outsiders, more senior researchers, but outsiders to the field, this book is aimed to be very accessible to them and to get them off the ground, to get started on some important questions.
Yeah, so that's target audience. Very good. And I know it's a little early because the book just came out, but I'll ask it anyway. Where does this go, let's say, over the next couple of years? And you touched on several, new missions going up, new laboratory astrophysics going up. But just sort of, where might this head over the next 2 years? Are you planning in Exoplanets 2 ebook, or too early for that?
It's a bit too early for that. A book like this is a huge effort. It took several years, as I mentioned earlier, and commitment from numerous people, very busy people across the field. So
it's still relatively compact at about 300 odd pages or so, right? It's not 1,000-page, book or something like that. So it's concise.
Yeah, I mean, that was the goal. The request to the authors was very specific, is to keep it compact so anyone with interest in any one chapter can read it in one afternoon, very quickly. So the goal was that, but that also takes a lot of effort to write.
Yes.
Writing that compact, concise way, it takes a lot of effort. So I don't know when there would be, if and when there would be a second version, but I hope until then, I hope the content of this book will last, will be
at least that long.
At least that long.
At least.
We have tried to be future looking. So at least what's happening in this decade, at least for the next 5 years or so, we should be pretty accurate, and then we'll see. But I'm looking forward, very excited to see what's coming in exoplanet science with all my colleagues in the field are doing great work in pushing the frontiers of this field. So I think this is a testament to the success of all of us in doing what we can.
Yeah, this is going to be a super exciting field over the next decade or so, for sure.
Absolutely. So my best of luck to all the young people and anyone who wants to do exoplanet science.
Yeah, like me.
Yeah. And to humanity.
Very cool, very cool. All right, Madhu, thank you so much. And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Thanks, Frank. Bye.